previous videos, we have talked about the task of forward kinematics, which is if I give you the joint variables, you give me back the location and the orientation of the end effector with respect to an inertial frame. Now here we are going to talk about the inverse kinematics problem, which is basically the opposite of that. I give you where the end effector has to be and the orientation of that with respect to the base frame. You tell me what joint angles I need to have to make it possible. Okay, so in the inverse kinematics problem, I'm going to, as I said, give you the rotation matrix of the end effector with respect to the inertial frame, or you can say R of n with respect to 0, 6, n, whatever. That's another way you can do it. So it's up to you, right? You can also say R of n, where n is the coordinate frame attached to the end effector with respect to 0, which is the base frame, as I said, or as I said, E of R of E with respect to I. One of these I give you, right? They're the same thing. And also what? I also give you D or O, the origin of the end effector with respect to the inertial frame. Or you might call it in this case D of N with respect to 0, correct? So if I give you this, you give me the joint angles. And I can show all of the joint angles as QIs. Okay, I can show them as QIs, where I is going from 1 to n. So I go from the workspace back to what? To the Q space, to the joint space. And as I said, this task is called inverse kinematics. If you remember, if I go from the joints to the end effector position orientation, we call that what? Forward kinematics. And we learned that for forward kinematics, you can find unique solutions. And I introduced you two different methods. One of them was the Dinowitz-Hartenberg convention, and the other one was vector addition method. And there are other methods too. The good thing about forward kinematics is you can always find a unique solution as long as what? As long as these joint variables are within your mechanical limits, right? Because you know each joint naturally can have some mechanical limits. If you have a rotary joint, it doesn't mean it can always rotate full 360 degrees. And if you have a prismatic joint, it doesn't mean it can just move forward or backward as much as you want. There are some mechanical, physical limitations. So as long as the Q values that you provide to the forward kinematic task are within the limits of the joint mechanical limitations, then you should be able to get a unique solution for the rotation and the position vector of the end effector in basics. Inverse kinematics, on the other hand, it means what? It means really solving a bunch of nonlinear equations. Why? For example, if I give you this Stanford arm, which you can see here, and I give you the homogeneous transformation matrix of end effector with respect to base, where, as you know, this 3x3 portion of it is your rotation matrix, and this 3x1 portion of it is the end effector position. If I give you this and say, hey, what angles and what value for this prismatic, this guy I need, so you know there are 6 variables in this, right? Theta 1, theta 2, d3, and then theta 4, 5, and 6 for the spherical. So I have 6 joint variables, it has 6 degrees of freedom. I give you the rotation matrix and I give you the position of the end effector in base. I say, you give me the 6 variables that can make it possible. Well, what does it mean? Well, it means that you have to find this homogeneous transformation matrix in general as a function of what? The 6 joint variables. And if you do, the components here for the entries here are shown on the right side of the formula. For example, this element 1, 1 of the rotation matrix, this is something like that. It is a function of what? Angle 1, angle 2, angle 4, 5, and 6, right? So it is a function of 5 angles, all of them, except for D3, it is a function of all of them. Similar thing you can say for element what? 2, 1, if you look at element 2, 1, you see that's this guy, element 3, 1, that's this one. And so you go to next column, and then you go to next column, and then you get what? These 9 elements here that you can see. So this guy here is like element 3, 3. Not all of these 9 elements of the rotation matrix are the function of all 5 angles. Some of them are, some of them are not. But probably if you look at even the simplest case, which is this element 3, 3, you clearly see it is a function of 3 angles, 2, 4, and 5. And then these components of the position vector, you see, they are now functions of what? They are functions of not only the joint variables, they are also the function of this displacement d3 here. By the way, this d2 and d6 that you see here, they are just constants for the geometry of the robot. Okay, so one of them is this d6 that you have in the wrist, and the other one is this guy here. So they are fixed distances, but d3 now that's a variable. So now, if you look at this set of equations that I have to solve, how many equations do you see here? Well, you see 12 equations, right? Because this guy has 9 entries, this one has 3. So you have 12 equations, and how many unknowns you have? You have 6 unknowns. Okay, so first of all, your system of equations and unknowns is not square. It is over-constrained, right? Because you have more equations than unknowns. And it means that you do not need to satisfy all of these at the same time. You know, a rotation matrix has a magnitude of 1, and the columns are perpendicular to each other, but writing those constraints of the rotation matrix, it means that, for example, I have to consider the first 3 guys as a vector, then the next 3 as another vector, and then say dot product of them is 0. So those constraints, if you want to add them, it's even scarier. So first of all, the system is over-constrained. So if you want to, if it was a linear system, you had to use the pseudo-inverse, and you had to find the least square solution or something. Right? So does it mean that you cannot find the exact solution? You can, because, as I said, although it looks like you have 12 equations, but these are not 12 linearly independent equations. The equations do depend on each other. So although you have more equations than unknowns, it doesn't mean that you can never get all of this satisfied. You can, because there are 6 constraints, right? So there are 6 constraints between the elements of the R matrix. But writing those and then trying to, using those, get rid of 6 of this equation is a very daunting task. Okay, so even if I give you only 6 of these and say, hey, here, there's 6 and that 6, just use a subset of this and try to solve it, right? Just use the 6 of them. The 3 O's, the 3 for D's, and then 3 of these R's, okay? Even if I give you that, how would you solve it? The problem is these equations are highly nonlinear. You do not have the angle itself, you have sine and cosine of it. You have this unknown variable d3 multiplied by sine of something else, so they are highly nonlinear. They involve sine and cosine, we call them transcendental equations. And solving them is analytically most of the time close to impossible. Okay, so and I'll show you one very simple example here. So forget about solving this. If you just even try to solve something as simple as the 2 degree of freedom planar arm. If you remember, in a 2 degree of freedom planar arm, the x of this endpoint, which you can attach to it the end effector if you want, The x of the end effector, if you remember, it is equal to a1 times cosine of angle 1 plus a2 times cosine of angle 1 plus 2, c1, 2, if you remember, that's cosine of theta 1 plus theta 2. And then the y of the end effector is a1 times sine of 1 plus a2 times sine of 1, 2. Okay, so now if I give you xe and ye and then say what is theta 1 and theta 2 that are hidden inside the sines and cosines, how can you solve these simple two equations, two unknown set of equations for me, right? 2 and 2. It's a square system, but here I clearly have nonlinear terms, cosine of 1, cosine of 1 plus 2, and so on. Right? If I try to give this and ask MATLAB to solve this analytically for me, what do you think MATLAB will do? Is it going to give me some nice analytical formula back? Well, let's try it. So here, this is what I have. Instead of L1 and L2, I just call them A1 and A2, but it doesn't matter. If I want, I can replace this with A1, correct? And then here, this is going to be A1. So it's not going to change anything really. I just call them L1 and L2, but here, just to be exactly like that. So here I call them A1 and A2, okay? For theta 1 and theta 2, I use T1 and T2 just to make it shorter, and then X and Y. You see my equations? This is the first equation, this is the second equation. I'm trying to use symbolic bulldogs to solve it analytically for me. And then I say, hey, solve those for theta 1 and theta 2 for me, right? And then I enter, and I expect MATLAB to return two nice formulas for me. And guess what? When I go and look at my MATLAB, after I wait a little bit, it gives me what? Say, T1 is this, T2 is that. Gosh, there we go. I've got some solution now, right? And then I say, okay, fine, what is T1? Say it's T1. What is T2? That's T2. You know what it means? It means I couldn't solve it. I'm sorry. I could not solve it. I recognize that there should be two solutions, but I cannot really solve it for you. Okay, so do not count on the software packages to give you some nice, fancy analytical formula. Now, some software packages are a little bit better than others. Like, for example, for analytical, as far as I know, the software called Maple is better than MATLAB. But still, it doesn't mean that it might or might not be able to solve this. But when you give it something like that, I would tell you any software package is not going to do anything for you and returns nice formulas for you. Okay, it's not going to happen. So, what can we do? We still want to solve the inverse kinematic problem, but we want to solve it in this video analytically. Can we do it? Yes, we need to use a little bit of geometry. Can we do it for every robot? No. It depends on the type of the robot, but some conditions we'll discuss. So analytical kinematic, inverse kinematic solution in general is not always possible. For some specific conditions, it is possible. We'll talk about it and we'll see when. And we provide some examples here. But this is not the task we can always do because it involves highly nonlinear coupled set of equations together. The other important thing about inverse kinematics is it does not have a unique solution necessarily. Okay, I can show you that your inverse kinematic solution in general can have no solution at all, a unique solution, or several solutions. Okay, right? Sometimes it can have infinitely many solutions. So let me write that for you here because this is important. So while the forward kinematics problem has a unique solution, we say as long as the joint variables are within their mechanical limits. The inverse kinematics problem can have solution, a unique solution, many solutions, or let's say several solutions, and infinitely many solutions. Okay, so that is the difference, that you're not dealing with a problem with a unique solution. It's not going to be the case in general. So that is very important, and I'll show you. When is it that you get the unique? When is it that you get the none? When is it that you get several? When is it that you get the infinitely many? We're going to discuss all of those scenarios in this video. Okay, so to do that, let's just start with some simple example, which I just mentioned. So here you have the 2 degree of freedom planar arm, and the equations of forward kinematics for this guy are quite simple, right? And we had that in our forward kinematics lecture, so I just wrote them down here. The derivation of that is done already in the previous videos. So this is my 2 degree of freedom planar arm. You see here, that is my first link. And then I have my second link, which is rigidly attached to the end effector. The second link and first link are pivoted at this point, and the first link is pivoted at this point. And here I can give names to these points if I want. So that end effector point, I call it point E, for which the coordinates are given. The joint between the 2 links, I might call it point, let's say, A, and the origin, I might call it point O. Okay, so here I provide some names. The length of the members are A1 and A2. The angles are θ1 and θ2, where θ2 is measured with respect to the extension of member 1, not absolute. And if A1 and A2 are given, so not only X and Y are given, also actually A1 and A2 are also what? Given. And your goal is to find what? θ1 and θ2, which can give you such position of the end effector. You might say, what about the orientation of the end effector? Well, in this case, because the end effector is rigidly attached, so here there is like welding. Okay, the end effector is rigidly attached to the second member. So orientation of the second member is going to be the same as orientation of the end effector. And clearly you know that the angle of the second member here from the horizontal axis, this angle is what? θ1 plus θ2. So that is the orientation of the end effector. In other words, the orientation of the end effector, if I want to call it rotation matrix of the end effector with respect to the base, it is a rotation Z with angle what? The angle is θ1 plus θ2. Okay? So once you know θ1 and θ2, the orientation is fixed. You don't need to be worried about that. So in this case, all you really need to care about is the position. Because again, the end effector is not separate. There is no joint here between this end effector and the second link. So it's not going to need this second, so you need the first frame here, you need the second frame here at point A. At E, you really do not need an extra coordinate. Okay, so 2 equations and 2 unknowns here, you clearly can see. And, well, you saw that MATLAB did not give me too much of help, so you say, well, can I solve it myself now using what I know from my algebra, hopefully. And, well, let's find out if you know. So here, these are the equations. And now, how can we solve it? Well, there are 2 ways we can solve this problem. Method 1 is we try to really use our algebra knowledge and try to solve this problem. Method 2 is geometrically. And the geometric method in this case is easier. So first I will show you how to solve this geometrically. And then if I see the video is not getting super long, then I'll also show you the algebraic method, which should give you the exact solution. And the reason is I need to look at the Scara robot and talk about the Scara. And then also I need to talk about when is it that you can do what we call kinematics decoupling, and talk about the special 60OF elbow robots, or the articulated robots. So there are a bunch of things we have to discuss. And as I said, first let's do the geometry, okay? Now here, I'll try to clean this up to provide some room to write whatever I want on it. So as I said, I call this point O, I call this guy here A, that point over there is E, and now the goal is to find theta 1 and theta 2, this x of E and y of E are given to me. Okay, so the first thing I do is this. I draw a perpendicular from point E to the extension of the first member. So I extend the first member, and from E I draw a perpendicular to it, and I will call this point B. Hopefully so far so good. Now, what do I do? I try to get this angle first. What is this angle here in red? What is this guy? Can I find this angle? And the answer is yes. If I look at the triangle OEA, the triangle OEA looks like this, where this is A1, this is A2. What is this angle here in terms of theta? You know, when that is theta, the whole thing is pi, so that is pi minus theta 2, correct? And what is this second side, which is shown here by C? Well, C, if you look at this triangle OE and this point here, whatever it is what you want to call, maybe you call it point C. If you look at OEC, which is a triangle, you see that OE squared is OC squared plus what? CE squared. Right? And OC is x of E, and CE is y of E. So this guy here should be the square root of what? It is the square root of x of E squared plus y of E squared, right? This is what you have for this triangle. Okay, so this is my triangle, as I said, O, A, E. Now, in a triangle where A1 is given, because you know A1, A2 is given, and this square root is also given because x and y are given. If I know all the three sides, can I find this angle? And the answer is sure I can. What is it? I use here the law of cosine. The law of cosine says any side squared is equal to sum of the two other sides squared minus 2 times, or plus 2 times actually. Well, let me make sure. No, it is minus. Minus 2 times A1 times A2 times cosine of angle in between, which in this case is pi minus theta 2. So this is what? This is law of cosine. Okay, there are 3 laws like this that you can write like any arbitrary triangle, and then 3 laws that you call laws of sine. And if you forgot about them, just go to my channel. Here is my channel. I'm going to go under engineering mathematics, and then there should be one which talks about laws of sine and cosine. You can see it here. And some other useful things, math tools that engineers need to know. Okay, so I explained that in practice with this rule. So here we are. Now, cosine of any angle subtracted from pi, from 3, is that this is the negative cosine of theta 2. Okay, so these two negatives can go away, and then from here, since the a1, a2, and this square root is known, then by the way, the square root and the 2 cancel. From here, you can find cosine of theta 2. It is going to be xe squared plus ye squared minus a1 squared minus a2 squared divided by 2a1, a2. Okay, and so this here should give me what? Should give me cosine of one of the unknown angles, cosine of theta 2. And here you might be saying, well, that's fine, so now theta 2 is going to be cosine inverse of this guy here. And you're right, it is. There is one problem though with the cosine inverse. Cosine inverse, sine inverse, and tangent inverse, if you remember in my previous videos I talked about them, they are not quadrant corrected. They are not sensitive to the quadrant, okay? So they are not going to give you the exact angle that you want. So instead of me taking cosine inverse, as I said in robotics, we always try to use what? Arctangent 2, because this one is quadrant corrected. So that is my preferred inverse harmonic function that I always want to use. So instead of cosine inverse, can I somehow do tangent inverse? And the answer is yes. But you know, the tangent inverse, if you remember, you have to give to it what? The sine of the angle and what? The cosine of the angle. You have to pass to it 2 entries. And the cosine of it I already have. But sine, as you know, is what? Plus minus 1 minus cosine squared, correct? So I can, from cosine, I can find sine, and then so I can plug it in here. Of course, it's going to give me 2 answers, one for plus, one for minus. Okay? So that's exactly what I'm going to do here. Instead of trying to solve this, I would call this ratio here, this ratio, I can give it a name. I might, for example, call this whole ratio here d. Okay, just call it d. From here, clearly sine of theta 2 is going to be what? It is going to be plus and minus 1 minus d squared under the square root. And then from here, I can find my theta 2. Theta 2 is arctangent 2 of what? D and, or sorry, plus minus square root of 1 minus d squared and d. There we go. So this is what? This is one of the angles, theta 2, where d here is this ratio. So if we define d as that ratio, which is a known number because everything in it is given, then clearly I can plug it here and I can get theta 2. Clearly there are 2 solutions. And now that I have theta 2, let's go back and see if we can find what? Theta 1. So we go back to this case here and see if we can find what? Theta 1. Well, I can find theta 1 as well. For theta 1, the angle I'm going to focus on is this angle here in green. What is this angle? This angle is theta 1 plus this angle, small angle here. If I know this angle shown in black, and I give it just some name, whatever you want. So let me call, for example, this angle as beta. then clearly this guy, this whole thing is going to be what? Theta 1 plus beta, correct? Now my question is, do you know how I can find this theta 1 plus beta? And the answer is clear. Sure I can. If I look at the triangle OEC, the same triangle we found this hypotenuse from. If I look at this triangle, the side in front of it is y of e, the side adjacent to it is x of e. So I can say this is arctangent 2 of what? Y of e and x of e, correct? So the sum of that angle beta and theta 1, which I'm about to find, is arctangent of y e and x e, and this is a given value because y e and x e are known. Good. So if I somehow can find beta and subtract it from both sides of this equation, that gives me theta 1, which I'm looking for. Now the question is, how do I find beta? Well, for beta, you need to look at this triangle OEB, the right triangle what? OEB. Where here is the angle beta. Okay, can I find it through here? Well, for that, I need to know EB and OB. If I know EB and OB, sure, then I can find beta. The question is, how do I find them? Well, if I want to find EB, I look at this triangle now. This triangle EAB. EB that I'm looking into is in front of the angle theta 2. This side from A to D is A2. Therefore, I can say the distance from A to D is what? A2 times cosine of theta 2, and the distance from E to D is A2 sine of theta 2, correct? So I can clearly find the length of EB, which I'm after, and I can also find the size of AB, which I also need. So EB here, this guy that I was looking after, this is A2 times sine of theta 2. Got that? Good. What about O2B? Well, if you look at OB, it is made of OA and AB. OA is clearly A1, right? So it is A1 plus the distance from A to B, which as I know is A2 cosine theta 2. So if I write it here, you see that OB is A1 plus A2 cosine theta 2, EB is what? A2 sine theta 2, and therefore beta can be written as arctangent 2 of the in front, which is A2 sine theta 2, and the adjacent, which is A1 plus A2 cosine of theta 2. There we go. I found beta. And so, if I call this equation 1 and I call this equation 2, if I plug 2 into 1 and subtract on both sides, that will give me my theta 1. So from 1 and 2, I can get my theta 1 to be arctangent 2 of YE and XE minus arctangent 2 of a 2 sine of theta 2 and A1 plus A2 cosine of theta 2. And this is my what? This is my theta 1. Done. I got them both. Now, do I need sine and cosine of theta 2 that I need in this formula? Sure, because I already have what? Theta 2 calculated in step number 1, so I can get the sine and cosine. So these two are going to provide me the analytic solution for theta 1 and theta 2 based on the given parameters. And as you can see, I only use arctangent 2 in it to make it quadrant correct. Now, let's look at the number of solutions. As I said, the number of solutions is what? 2. There is a plus and a minus. So in general, there are what? 2 solutions. And what are those 2 solutions? So if this is my robot, and this is this point, and I can get to the point like this. Use a different color for this member. Okay, so I can get to this green point, which is the end effector location, the desired end effector location. I can get to that green point using what? Using this configuration. Where here, this is angle theta 1. And this angle here is what? Theta 2. You can see they're both positive, both counterclockwise. This is one way that I can reach what? I can reach the desired location. Now the question is that the only way? And the answer is no. There is a second solution. As you can see, there are 2 theta 2s, and if I plug in each one of them in theta 1, it gives me a separate theta 1. So in general, there are 2 pairs of solutions. One of them is like this, the other one looks like this one. Okay, where here, theta 1 is a bigger angle, positive. But if you look at theta 2, you have to extend member 1, and then from that, get back to member 2. Clearly, you see theta 2 here is what? Negative is clockwise. That corresponds to the negative square root. This one corresponds to the positive square root. So as you can see, in general, there are what? There are 2 solutions. There are 2 solutions. And then, in general, and then we call this solution here, this configuration, one name, and then this other configuration here, we give it another name. Okay, so we call this one elbow down, and we call this guy elbow up. Where elbow here is this point in black. So this point here in black, we call it elbow. One of them is down, one of them is up. Okay, so in general, there are 2 solutions, elbow up and elbow down. Good, so I showed you that there are 2 solutions in general. Elbow up and elbow down. But could be any case that there is no solution, or there is, let's say, a unique solution? Yes. What are those? So one case here is that, so here, as I said, 2 solutions. Now, could be a case of unique or no solution? Yes. With the very same robot, what is the maximum point it can reach radially? If I ask you, what is the reach of this robot? What is the largest distance, the biggest distance from the base of the robot that this robot can reach. You say, well, the max it can reach is here, that you extend this second member and you make it fully extended like that, correct? And you're right. That is the max the robot can potentially reach. Agree? Now, if I say, well, I want my end effector here. So I again say, this is what? This is y of e and this is x of e that I want you to be. Can you reach there? Well, the answer is no. It's outside the what? The workspace of the robot. So when the end effector that I want is outside the end effector of the robot, it's not going to be reachable. Correct? So if my point is here, guess what? There is no solution because I cannot reach it. On the other hand, if I ask you, what is the minimum reach of the robot? In other words, how close can the end effector of the robot be with respect to the origin? How close to the origin can the end effector go and grab something? You say, well, that is when what? When this member, the second member, is fully retracted. In other words, it's come back like this here, like this guy here in green. If it's fully retracted, so in the first case, theta 2 is 0. In the second case, theta 2 is what? Pi, correct? Here, you see? This green case is the case that the red member comes back. All the way back. So if I choose my target point somewhere here, let's say, or here, forget about that, here. If I put my point E here, do you think you can reach it? The answer is no, you cannot. Because it's closer than what I can potentially reach. Okay, so in general, if here, if A2 is less than A1, if A2 is less than A1, then you can see in general there are two circles to consider. One of them is this circle. I can draw it for you. And the other one is this circle. Okay, in general, there are two circles centered at the base of the robot. And clearly, the radius for them, if I ask you, the radius for the big one is A1 plus A2, and the radius for the small one is A1 minus A2. As long as your end effector desired location is within these two circles, you can reach it. Once you get outside the big circle or inside the small circle, you cannot have any solution. So in this case, there is what? There is no solution because you are here, these areas in black. Any area here in black, there is no solution. As long as your end effector is in this black area, there is no solution. You can only have solution inside this disk, which, by the way, you call it what? This is the workspace of this robot, right? It's this. This donut is the workspace of the robot. So there is no solution when what? When the end effector is outside the workspace. There is no solution. In general, you have two solutions as long as you are what? Within. So here is that the end effector is what? Is inside the workspace. So if it's inside the workspace, you have two solutions. If it's outside the workspace, you have no solution. And then you might come and say, well, what if it's on the edge of the workspace? Like, what if it's here? What would you say? How can I get there? Well, I need my theta 1 to match this angle here, and my theta 2 to be what? 0. Or if it's on the edge here, I need my theta 1 again to match that angle, and theta 2 to be pi. Okay, in this scenario, there is only what? A unique solution. Okay, so you can see that I can have one solution, one unique solution, as long as the end effector here is on the workspace boundaries. Which clearly in this case means theta 2 is 0 or theta 2 is what? Pi, correct? Either it's on the big circle or it's on the small circle, theta 2 is pi. So you see that depending on where I pick the end effector, I can have one solution, no solution, and two solutions. Could I have infinitely many solutions? Well, not in this case, but in other cases, I'll show you that, yes, there are situations that you can have infinitely many solutions, and if you remember, we call them what? You're right, we call them singularities. So we're going to talk about that. Okay, so here is the case. Hopefully, it was rather clear what I'm doing. And, well, let's see. Okay, the other important thing is, in this case, the orientation is of no concern because it's automatically determined when I know theta 1 and 2. But in general, if you remember your workspace, when here we say inside the workspace, your workspace was two parts in general, if you remember. Reachable workspace and what? Dexterous workspace. You're right. So sometimes you can reach the point, but not at arbitrary angle like in this case. If you see, if I give you this point and I say reach it, you can, but all the orientation you can have are determined by this member number 2. That's the angle of 2 plus 1 or minus 1 in general, right? So the orientation here is not under your control. So here, any point in this workspace is pure reachable workspace. This robot does not have what? Dexterity. Okay, unless you add a third joint here and make it like a 3-degree of freedom, then you can access arbitrary angle. But in this case, and if we have time, I'll talk about the 3-degree of freedom planar arm as well. The solution of that is a little bit more geometrically involved, but the 2DOF does not have any dexterity. Good, so we solved this one simple example case. Now, I told you that if I can, I will solve these two guys analytically for you. And since I promised, let me do this. Okay, so here I'll try to go somewhere else and bring it here. Maybe I can solve these equations for you with algebra without any geometry like this. Is that a possibility? Let's take a look. So here, what I will do is I try to see if there is any way I can find theta 2, just like previous case. But first, for that, I need to expand this C12 and S12 from Triggs. So this is going to be A1 C1 plus A2 C1 2 cosine of 1 plus 2 is C1 C2 minus S1 S2 if you know from trigonometry. This is A1 S1 plus A2 times, this is going to be sine 1 cosine 2 plus cosine 1 sine 2. Okay, so here are the expanded versions. And now, this is what I'll try to do here, is, as you can see here, I have a cosine squared, I have sine squared, I have cosine squared, I have sine squared, and the answer is whether I can get one of them eliminated between the two. Right? Can I find theta 1 or sine or cosine of theta 1, eliminate it, and whether that can give me anything? Okay. So here, if I factor out the cosine of theta 1, you will get A1 plus A2 cosine 2. And if I do sine 1, the coefficient of that is negative A2 sine 2. In the bottom one, I factor out sine 1, it is going to be A1 plus A2 cosine 2 again. Correct? And then if I do cosine 1, it is going to be A2 sine 2. So you see, they are quite similar to each other. Right? This term is exactly there. This term here is quite similar, and I can even, if I want, I can write this as like a matrix format, right? And try to find one based on the other, right? And then come back and replace it in one of these equations. So if you want to write this as a matrix format, you can write it as or if I formatted it as one, it is going to be negative A2 sine theta 2 and A1 plus A2 cosine 2. And then again, A1 plus A2 cosine 2, and finally A2 sine 2. This thing times S1 and S2, or S1 and C1, I'm sorry, is going to give you XE and YE. Okay, and if you here try to solve it for S1 and C1, then it is going to give each one of them as a function of S2 and C2 and XE and YE. What you need is to invert this guy, and then multiply the inverse of that by this guy. That will give you sine 1 and cosine 1 in terms of angle 2. So if I do that one for you here, well, you know how to invert a 2 by 2 matrix. If you invert a 2 by 2 matrix, what you need is to negate the diagonal elements, swap the anti-diagonal elements, and divide by the inverse, correct? So if I call this A, call this X, and call this B, then I need A inverse, right? Because the solution X is A inverse times B, and A inverse, as I said, is and negate the diagonals, and then swap the anti-diagonals, which in this case the anti-diagonals are the same thing, so swapping or not swapping is not going to make any difference. Or wait, yeah, both of them are same. The divided by, of course, the determinant, which is the product of the diagonals minus the product of the anti-diagonals. That's the determinant. It is this one, and then the times, of course, x, e, and y. So if you do it, since x itself is S1 and C1, you will get two results. That S1 is going to be A2S2YE and plus A1 plus A2 cosine 2 times this is x, I'm sorry, divided by the determinant term, and then C1 is going to be something similar, except it is going to be this term here minus this one times YA, again divided by the determinant. And what is the determinant? If you want, you can simplify it a little bit. Because in the determinant, if you see this guy here and this one, since they're all going to be negative, it is negative, the A3 can be factored out. So the whole determinant, if you do it, it is going to be negative A1 squared, negative A2 squared. Negative A2 squared comes from these two terms, as I said, with the negative. And then negative 2A1 and A2C2, correct? That's what you have. Negative A1 squared, negative A2 squared, negative 2A1, A2C2. And so, what you can do is write that down here. So that is sine 1 and that is cosine 1. And so from here, theta 1, which is our tangent 2 of sine 1 and cosine 1, is going to be these two guys. Right? So you can just plug them in here. So this is one of them, and the other one is going to come to the other side. There we go. So now this formula here is theta 1. This is theta 1 based on theta 2. I mean, if you know theta 2, so you can calculate the sine of it and the cosine of it, this formula will exactly give you what theta 1. So we need to somehow find theta 2 individually without the need for theta 1. Can I find theta 2 individually? And the answer is yes, I'll show you. But if I know theta 1, this guy will give me, if I know theta 2, this one will give me theta 1. And if you look at the nature of this, actually, It is very similar to what we have here. I can even show you they are identical. Okay, it's not really hard to show you these two are identical. All you need here is to know how to subtract two arctangents from each other. If you can subtract two arctangents from each other, then I can show you this one is exactly this guy. Okay, so just you need to do a subtraction of arctangents, and I'll give you a hint here that arctangent 1 or A minus arctangent of B in general, if you know trigs, this is equal to what? Okay, the subtraction of two arctangents. If you don't know, just call it I. Take a tangent from both sides, then you see tangent of I is going to be tangent of A, tangent of something minus something else, which is tangent of first one. Minus tangent of the second one, in this case it's going to be A minus B, divided by what? 1 plus, correct? 1 plus tangent A tangent B, which is going to be A times B. Therefore, you see the result of this is going to be arctangent of A minus B divided by 1 plus AB. Okay, so if you call this guy A, and you call this guy B, and arctangent A minus arctangent B, instead of that, you replace it with this one, arctangent of A minus B over 1 plus AB. If you do that, I'm not going to do it, I'll leave it to you just as a practice. If you do it, you will exactly get this formula. Okay, so I could definitely get one of those two formulas I did in geometry, I could get it back here. Now the question is, where do I get this one? This theta 2, can I get this guy through the algebra? And the answer is yes, I can. I just need to go back to my original equations and see if there is any way that I can find a relation pure based on theta 2. Okay, is that such a possibility? Well, let's do that. So here, this is what I do. The first equation, it says x of e is equal to this. I call it equation 1. The second one, which says y of e is equal to this guy, I call it equation 2, if you don't mind. Then I'm going to square both sides of 1 and 2 and add them together. Add the left sides together, add the right sides together. Okay, and see what you get. So this is what I'm going to do. I'm going to square equation 1 and add it to the equation 2 squared. If I do that, on the left side, I will have xe squared plus ye squared. And what do I get on the left? I will get sine 1 squared times a1 plus a2 c2 the whole thing squared plus sine 1 squared times negative a2 sine 2 the whole thing squared. Agree? And then this is a plus b squared, so this is going to be plus 2 times ab times the product of the terms. And since this is a negative, actually, the negative can come out of the whole thing and make it like a negative of that. And so you get a to s2 times a1 plus a2 c2. So this is only the square of the first term. The square of the second term is also quite similar. That one is going to be, and if you don't mind, I'll write it down below here so that you can see it side by side. It's going to be s1 squared times this guy squared, and then plus, as you can see, C1 squared times A2 squared. And then again, plus 2 times them. Now here everything is positive, so you're going to get plus 2S1 C1 times A2S2 and times A1 plus A2C2. Okay, so each one of these guys is the square of one side of 1 and 2. I add them together. If I do that, what do I get? Here I get xe squared plus ye squared is equal to. These two terms are the same thing. They cancel out. One of them is positive, the other one is negative. If you look at these two terms in blue, they both share the similar term. If you factor it out, you will get sine 1 squared plus cosine 1 squared, which is 1. So the result is simply going to be A1 plus A2C2, the whole thing squared, right? As I said, times sine squared plus cosine squared, which is 1. And then here also, the A2S2 is the same in both of them. Negative or positive doesn't matter when you square it. The result is simply A2S2 squared. That's the result. And then one of them has sine 1 squared, the other one has cosine 1 squared. Again, it's going to be 1. So that's what you get. As simple as that. Now let me expand this one. So this is going to be A1 squared plus A2 squared cosine squared plus 2A1 A2 cosine 2 and then plus A2 sine 2 both squared. And again here you can combine these two terms into simply A2 squared if you factor out A2. And then all you need is take A1 and A2 to the other side, subtract them from X and Y, and divide both sides by 2A1, A2 to get what? C2. And if you do that, you will get exactly the same formula that we had the last time. Which is exactly this guy here. You see? So I could get that again, and if I call it D, then your theta 2 is going to be arctangent of plus minus square root 1 minus t squared, and D, which is, as I said, exactly like the previous case. So you should be able to get the exact same equations from algebra if you know algebra and tricks a little bit, but not too much. You should get the same formulas that you got for your from your geometry. Okay, so here we looked at the solution for the 2D of planar arm with two different approaches, algebra and geometry. We looked at different scenarios that under which conditions you have 1, 2, or no solution. And now I have a couple of other things to discuss, but since this video is going to be very long, I would rather stop the video right now and make the next video second part of Analytical Inverse Kinematics. So thank you for your attention. See you in my next part of Analytical Inverse Kinematics.